Okay, class, let me start our 14th lecture. We have discussed about the examination that we should have at the end of this trimester. The problem going to be 5 problem and 50 point. And the problem number 1, we have mentioned about this one is going to be the analysis of 2D or 3D structural statically determinate structure. It means the structure that can be analyzed by using the free body diagram and equation of equilibrium. And Ajahn also assign you guys to go back to the engine static and trying to review what you have learned from that course, and that means you should be able to analyze this kind of structure under combined loading. What is going to be the combined loading? For sure, after you have the structure, you draw the free body diagram, you use the equation of equilibrium, you may determine the reaction. And then the chapter 6, we have the equation of sigma equal to the moment, the internal moment, times y over I. And for chapter 7, you have tau equal to the internal shear. That is going to be the internal moment and internal shear force VQ over IT. So it requires you to draw the free body diagram and determine the internal force. For example, internal transverse shear force, internal moment, that's going to be the bending moment. And then you use the equation to determine both normal stress and shear stress. And at the end, you will get the stress element. You're going to have the sigma and also the how. And for the shear, if you have one shear on the stress element, you're supposed to have 4 of them. I'm given the lesson of this from our previous lecture. And the analysis also bases on the x and y axis. So this is going to be sigma sub x. This is going to be how sub xy. And we consider the first problem that's going to talking about the frame. This frame has the point A as the pin, point C as the pin, and also the B is the hinge of the pin. And if you consider this frame is subjected to the triangular load of 4 kilonewton per meter, the question they start by asking us to determine the reaction. If you consider the whole frame, you can see that by checking the member, you can see the member BC is the two forces member. Why? Why is the two force member? Because the point B and point C is the pin or the hinge, and between the point B and point C there is no forces. So that means the member BC is going to be the two force member. That means it's going to be in tension or it's going to be in compression. And also, if you consider how the structure reacts under the force, you can see that under the force, the beam AEDE is going to rotate, something like this. That means what? That means the member BC gonna react to balances. That means the force as the point B acting on the beam is going to be in this direction, is upward direction. That means the member BC gonna be in what's so-called incompression. If we consider this, we can start to draw the free body diagram of the beam. So we start by the free body diagram of the beam AEDB and the column of the BC. And then we will use the equation of equilibrium to determine the reaction that occur on the structure equilibrium. Okay, and by doing this, let's check how long is this one. Let's make it by do some kind of copy. Let's check this one is about 5 centimeter. So this one is going to be the beam. This point is A, this point is B, and make it half at point D, in which the load going to apply over here for 4 kilonewton per meter. So this is going to be the angular load and applies over here on the right hand side and over here on the left hand side. This is 4 kilonewton per meter. So also we supposed to set the XY reference axis. Let's say this one is the Y, this one is the X. And the beam ADB under the application of this force, as we mentioned, the force on the member BC gonna to resist in this direction to balance the rotation due to the angular load clockwise. This one supposed to be in the counterclockwise direction. So by setting things like this, our member BC is subjected to the compressive force, and then this is B, this is C. Let's set the force here as the F sub, and following this one, F sub BC, and then the A. The A is the pin. So the force as the A is supposed to be at the A sub Y, and in this direction is going to be A sub X. And then else, the distance, this is going to be 3 meter, this is going to be 3 meter. So according to this, we will have the length like this. And also what the direction of the member BC. This is 3 meter, this is 5 meter. So according to the ratio of here, as we know, this is going to be 3, this is 5. So everybody know that this is going to be 4. Okay, this is the free body diagram of the structure. And also, if you go further, the force F sub BC here is going to be what? Will you separate it? This is in vertical. This is 3. It's going to be 3 over what? Over 5. And then it's going to be F sub BC. And in another direction is here. Here is in horizontal direction. It's going to be F sub BC. And then this is 4. It's going to be 4 over 5 F sub BC. Okay, that is going to be very complete free body diagram of this. They ask us to determine the reaction at the support A and the joist B. That means for the A sub X, A sub Y, and F sub BC. By doing this, we have 3 equations of equilibrium. Summation of F sub X equal to 0, summation of F sub Y to 0, summation of F sub moment equal to 0. We start by taking the moment at point A to eliminate the unknown A sub X and A sub Y from our equation. So we can determine F sub BC easily. F sub BC, you can see this one produce no moment. It's point to the point A. This one going to produce the counterclockwise direction. So the first one is 3.5 F sub BC. And this one is 6 meter from point A. So we can see this one times 6 meter. And
the force that's X over here is supposed to be has the resultant force here due to the symmetry of the triangle. This is going to have the resultant force of 1/2 of 6 and times 4. If you push this one into the calculator, this one gonna be 3 and this one going to be exactly 12 kilonewton. So this one gonna be 12 kilonewton and this one 12 kilonewton is going to be 3 meter from point A. So it's going to be time 3 meter. So this one cut, this one to be 2. And then our F sub BC is equal to 12 and then time 5 for up and then divided by 6 and then this one cut you're going to get this one for 10 kilonewton. So the first one we obtain F sub BC is 10 kilonewton. Put the answer over here and then we still have need to find what summation of F sub x equal to 0. Okay, the summation of x sub x equal to 0. A sub x is in this direction, so a sub x is equal to what? This one equal to what? This one equal to this one, equal to 4 over 5. And then F sub BC is 10. So A sub x is 8 kilonewton. Okay, that is for the A sub x. Just put this one 8.0 kilonewton. Okay, and then what? And then we can find summation of what? Summation of F sub y equal to 0. So this one is upward positive. Our A sub y is upward. This guy is plus. This one is 0.6. This one is 10. This one is going to be 6 kilonewton. And then this is up equal to 12 kilonewton. So if you compute this one, you can get A sub y easily equal to 12 minus 6. That means 6 kilonewton for the A sub y. So put this one is 6.0 kilonewton. So we finish this calculation and then we get the reaction at point A and also the reaction at the joist B. So that means this one, we get this one for 10 kilonewton and this one also 10 kilonewton. So the resultant acting at the point C is 10 kilonewton. If we like to find the reaction C sub x, C sub y, I think I ask you guys to determine what is going to be the reaction C sub y. What is going to be the reaction of C sub x kilonewton? Give it at your assignment. Okay, and then later they ask us to determine the normal force and also the what's so called the shear force and also determine the bending moment at point E. So where is the point E? You get to go back and this is going to be the point E and the point E is at what? At the middle of the portion AD. So that means this is going to be the point E, 1.5 meter, and they are asked us to determine the internal forces and internal moment. We can do it by the same thing. We cut this one, we cut this portion of the beam, and we are going to draw the free body diagram. And second, draw the free body diagram of what? Of A, E, and what? And use equation of equilibrium to determine the N, the V, and the M. Okay, by cutting this, we got the portion of the beam like this, and then this one is A, this one the E. What we have is what? This is in the reference of XY axis. We know the force here, A sub y. the A sub y. We have previously of what? A sub y of 6 kilonewton. So this one is going to be 6 kilonewton. And we also have A sub x. A sub x is 8 kilonewton here. So this is 8 kilonewton. Under the application of this, we have the force, and then is the triangular force. And due to this, the value of force here going to be determined by using the triangular angle. By consider the slope, this is 4 divided by 3. So the slope, consider the slope, and this one going to be 4, and then divided by 3. The slope there is going equal to what? Equal to this one is W divided by half of this is 1.5 meter. So this is 1.5. So if you push it into the calculator, W is going to be what? 2 kilonewton per meter. So this is 2 kilonewton per meter. Okay, and this one cannot be in equilibrium without the what? Without the moment here. That is going to be m sub e. And if you go further, you're going to get this one for the v sub e. And the last one that we're going to have, this one is going to be n sub e. And following this is going to be very easy. Summation of x sub x equal to 0. This one is positive. So n sub e is going to be 8 kilonewton. Okay, that is the first one for 8 kilonewton. You can put this one for 8.0 kilonewton. And then if you do the summation of f sub y equal to 0, this is going to be downward. Our v sub e is downward. The force here also need to have the resultant. The resultant of this is going to be 1/2 of 1.5, and then this one is 2. So if you push it, it's going to be what? 1.5 kilonewton. So this is plus 1.5, and then it's going to be equal to what? This is v sub e. This is equal to 6 kilonewton. So this is 6 kilonewton. So by doing v sub e going to be 6 minus 1.5, and it's going to be 4.5 kilonewton at this section. So answer this. You're going to get this one for 4.5 kilonewton. Okay. And then the last one that we're going to have is the moment. You do the summation of the moment at point E, okay, and then equal to 0. Your moment is what? Your moment is counterclockwise, is positive. Your m sub e in this direction. If you take this one also in the same direction, plus 1.5. However, the distance here is what? Is only 1/3 of 1.5. So it's going to be 1.5 divided by 3, which is going to be 0.5 meter. And this is going to balance by this one. This way is clockwise, counterclockwise. So it's 6 kilonewton, and the distance is 1.5 meter. You put them into your calculator. Your m sub e can be determined easily as 8.25 kilonewton meter, and it is positive moment. Positive moment going to produce this kind of deformation. The top is going to be in compression. The bottom going to be in tension. Okay, that's going to help you. The shear is downward. Okay, this is positive, is downward. That means the shear stress gonna be in this downward direction. So answer this one. You got this one as 0.25 kilonewton meter. Okay, now you move to the mechanics of material. The knowledge that we work on this portion of this problem is the engineering static. So we come to what we have. This time they ask us to determine two things. One is the transverse normal stress distribution. This the distribution of transverse normal stress. Another one is the what's so called, I think this one's supposed to be normal stress. This should be has to be normal stress distribution. Is the distribution of the normal stress or the distribution of sigma. This is the distribution of tau. Okay, this one is not kind of correct. Okay, this is going to be the normal stress. And from the equation that you have on the top, this is normal stress due to what? Due to the n sub e. This is the normal stress due to the moment m sub e. So the normal stress will come from two portions. However, the shear stress comes from this. This is for the chapter 7. This is for the chapter 6. You got to go back and review it. This is for the chapter 1. Okay? By doing this, what we have, let's go by finding the normal stress first. Okay? And by doing this, that is going to compose two things. One is going to be equal to. One is going to be the normal stress due to the bending, and this one is going to be the bending. Another one is going to be plus another one that's going to be from the normal stress. So this one is going to be sigma equal to my over I, and this one is going to be sigma equal to n, this one n sub e divided by a. This is m sub e. Okay, and you know that due to the bending, something like this, the one this is in the compression, this one is in the tension. Okay, and then there is some points that's in between of this. This is 2.5 centimeters, so this is going to be a half of this. This point going to be the point of zero stress. And then this one, let's say this one is going to be, if you put this one very big one, this is going to be compression, and this one going to be the stress, something like this. This one is in compression. This is compression. Okay, this is going to be in tension. And also due to the double symmetry of the section, this one going to be equal and in tension. We have this one and this one. Okay, this is occur passing through the point of the centroid of the section, and then we call this one as the neutral axis. Okay, neutral axis, or NEU. Neutral is the middle, and then axis. And then what we have is this is in tension. This is in tension. The N is what? Is compression. Okay, the N is compression, which means it's going to produce compressive stress. And then due to from the knowledge from chapter 1, due to this N, the stress occur on the section could be averages and computed by this equation. Okay, let's see. What is this going to be? Okay, this is sigma going to be. This is the normal, the momentary, the moment here is 8,250, and then this is Newton meter. Okay, and then the y is the distance you measure from the neutral axis to the top and to the bottom. This guy has the same one. Okay, same one of what? We have the section. If you recall from what we have on the top, just put it over here to be the reference. This is going to be 50 millimeter, and the depth going to be 100 millimeter. Half of this going to be 50 and 50. So this is the section that we are interested in without going back to the top. Okay, this is going to be 50 millimeter. This is 50 millimeter. And this is again is the neutral axis. This is the centroid of the section. That means of what? That means this one going to be 50 millimeter. This one also 50 millimeter. So what we have now is just put this one into the equation 0.050 meter, and then we have what? The I. The I is going to be I sub NA is going to be 50. Okay, that is going to be 0.05, and then 0.1. This is 100 millimeter cube, and then divided by 12. If you put this into calculator, this one going 4.167 and 10 minus 6 meter power 4. So you put this one 4.167 10 minus 6 meter power 4. So this one cut power 4 change to power 2. That is going to be Newton per meter power 2. If you put this thing together, you may get this one as what? Okay, 99.0 10 power 6 Newton per square meter, or it's going to be 99.0 megapascal. So that is going to be 99 megapascal. This one also 99 megapascal. And then we come to the axial stress. That's due to the N sub E. Okay, N sub E is what? N sub E is 8,000 Newton. That is 8,000 Newton. If you divide the section by millimeter, that is going to be 50 and then 100 millimeter square. And you know Newton per square millimeter, you got this one in the megapascal. So put them together, you get this one is 1.60 megapascal. Okay, and this is what? This is compression. This is what? This is also in compression. So it's going to be add up. So this one is in tension. However, this one is in compression. This one will be reduced. By combine them together on the chapter 8, we can combine this thing together based on the assumption of linear elastic. Okay, we can combine stress together and very small deformation. Very small deformation. That's going to be follow our study. And then the stress over here gonna be add up. This is going to be 1.6 megapascal plus 99. This is going to be 99.1.6. That is going to be 100.6 megapascal. So this is going to be large compression. Okay, and then what? On the bottom, this is tension, this is compression, is going to be reduced by 99 minus 1.6. Okay, 99 minus 1.6. That is going to be 97.4. This is going to be in tension, but smaller than that. That is 99 minus 1.6. That is 97.4 megapascal. And at the middle, now, what we have is what? This is going to be 0. This is going to be 1.6. So this is going to be stress in compression. By doing this, you can draw the triangle again. But this time, what we have is the neutral axis chip from the red line to the dash blue line, and this one is going to be the tension. So now our stress distribution by the combine of normal stress due to the moment and normal stress due to the axial force, we get the new one of the normal stress distribution as required. But the problem is the neutral axis right now change, And usually we just set following this. We just set this one. Let's set this one as the distance of y. And the total length of this is 100. That means the position here will be 100 minus y. We can determine the location. We can determine the location of new neutral axis by using the similar triangle. Okay, by similar triangle, you can see this is going to be 100 minus y, and this is going to be the distance of y. So 100.6 is going to be here divided by 100 minus y, and this is going to be equal to the slope here 97.4, and then divided by over here distance of y. If you push everything in your calculator, the new location of the y is going to be 49.2 millimeter. This is the position of this. This is going to be 49.2 millimeter if you measure from the bottom. Okay, you can get this, and this is going to be the normal stress distribution. We still have one more. Is this one? Is the shear stress. Due to the symmetry of this, the equation that we use to compute the normal stress is based on tau equal to VQ over IT. Okay, the V on the section, the V on the section always the same. It's going to be V sub E. The I on section also the same. The I is the same. And the T, now the problem, the T is the width of the section. The T also the same. So what is going to control this equation is the Q. Okay, Q is the area above what we find the tau. If we like to find the tau here, the area above here is 0. So the moment, the Q is the moment of the area above neutral axis is 0. So usually we know that on the top and the bottom and always like this of the section, we have the tau equal to 0. And then if you go back to the PowerPoint of chapter 7, the Q is what's so called the area. Okay, and then times the D, and you can see the Q is in the dimension of length power 3, and since this one change with the Q, so the curve of this is always what? Always have the curve like parabolic equation. As you know, due to the parabolic equation, the curve will have the shape like this. Okay, due to the symmetry, the top and the portion gonna have the same what? Same shape. And the tau max for this is gonna occur when the area is maximum. The area is maximum is occur as the previous neutral axis. So this is the point of tau max. Okay, and if you further to the chapter 7, tau max can be easily for the design. Tau max can be determined from 1.5 V sub E divided by A. And if you do this, it's going to be 1.5 V sub E is what? 4,500 Newton. And then divided by the area. The area is 50 times 100 millimeters square. 50 times 100. This is millimeters square. This is Newton. The unit of Newton per square millimeter is going to be in Mech Pascal. Okay, we can see and put the number into the calculator. This is going to be 1.5. okay อาจารย์ if I use this equation to find this how can I do it okay don't worry this tau at what tau max will form what we form this one v sub e and then it will be come from q max divided by I and then what another one is the t okay the point we are looking for produce the maximum q again is here that means what again we put this one 4,500 Newton 4,500 Newton that is going to be V sub E and divided by I is 4.167 10 minus 6 and then meter power 4 the width is this one that is going to be 50 millimeter so put this one for 0.0 meter now the problem is to determine the Q again the Q is the area let's put this area here okay and then the area is going to take the moment from the centroid of this area to the neutral axis of the section so this is going to be 50 millimeter this is going to be 50 millimeter that is 0.05 times 0.05 and then what the distance here is going to be half of the 50 millimeter from here to here that is going to be 0.025 and then you put them together and do some calculation you will get tau max in this one as what 1.35 megapascal again okay and then they ask us further to draw the stress element okay find the stress as point E okay find the stress at point E point E is what point E is in this direction point E is about this okay this is what 20 millimeter so the top portion of this is going to be 30 millimeter okay sorry okay if that case we just find what the point is supposed to be about here okay you measure what 20 millimeter from the bottom here so we have to determine this is going to be tau sub e and this is gonna be sigma sub e okay and the tau sub e as we discussed before the v sub e is downward when e sub v is downward so the tau here is going to be have the downward direction also that means the shear here going to be in this direction that is tau sub e and as you may know for the tau if this one down this one must be up to balance the force in the vertical direction and if you take the moment here see the red has produced a moment the blue gonna produce clockwise so we need this one to balance it and then here they come you got to have the horizontal balance by this one this is going to be tau sub e okay that is going to be in downward direction and also this one sigma sub e is in tension that's for sure over here that is going to be the stress that is going to be sigma sub e in tension and this sigma sub e also called sigma sub x and also tau sub e is called tau sub xy because we consider this is the x and this is the y and this is point e so what is the value of this Okay, by doing this, you can compute sigma sub e in two ways. One, go back and use this equation. Okay, or another one, you use the similar triangle. Okay, by using similar triangle, this is sigma sub e. You may have this is sigma sub e, and the distance you have here is what? This is 49.2, and this is going to be 20. So that is going to be the distance here and here, 49.2 minus 20. And that's one going to equal to this one, 97.4 divided by the whole length here of y, 49.2. Okay, by doing this, you push them into your calculator. Your sigma sub y gonna be 57.81 megapascal. Okay, that's very easy to find, right? Okay, next, the tau sub e, tau sub e, you must compute basis on this same thing. Okay, it's going to be v sub e, 4,500 Newton, and then the same thing divided by the same RIT, 4.167 10 minus 6 meter power 4 and 0.05 meter. The change is going to be the area. Now, at this point, the area you are considering is going to be here. The area going to be here. The area is what? This is 20 millimeter. This is 50 millimeter. So 0.02 times 0.05. And then what we are looking for is the distance from the centroid of the section measure to the neutral axis. Okay, by doing this, this is a total of 50 millimeter. This is 20. Half of this here is going to be 10, right? So this is going to be 50, the total, minus this one, minus 10. This is going to be 40. So this is going to be 4040, and then all of this is going to be in meter. If you push everything in your calculator, this is 0.864 megapascal. Okay, this is going to be your answer. This is going to be 0.864 megapascal. Okay. And then I would like to make the assignment for you guys. If you prefer, if you tie, please go back and tie the other point. This is the point E. Let's say if you put this one another 20 millimeter, and then can you find the stress element here? Okay, or if you measure this one for 25 millimeter at this point, can you determine the stress element for that point? The stress element is always the question that we looking for, because after this we will use the knowledge of stress transformation to determine the principal stress, to determine the maximum shear stress. Okay, let me finish this problem here. Let us work on the problem number 2 of the extra problem. In this problem, we have the simple beam. This simple beam has the pin support on the left and the lower support on the right. And the section is here, and it has the area of 700 square millimeter. This is structural steel section, and the I sub x of 513,333 millimeter. If also you like to have this in the meter power 4, that means you're going to have this one, let's say 10 power 6 millimeter power 4. 1, 2, 3, 4, 5, 6. Okay. And if you like to make it to be meter power 4, you got to divide this one by 10 power 12. The factor of 10 power 12 come from what? You know that, right? Okay, that is going to be 333, 10 minus 6 in meter power 4. And this beam is going to subjected to the loading of 3 kilonewton per meter. By doing this, they ask us to determine the internal force and the internal moment that occur on the section AA. That means they ask us to determine this. Before we can find the internal forces and internal loading, we got to draw the free body diagram of the beam, and then we will find the reaction first. When we find the reaction, we can find the internal forces and moment. By doing this, that means we got to draw the free body diagram of the beam. Is going to has, let's see, this is A, B, this is C, this is D, under the application of distributed load given here of 3 kilonewton per meter and has the X and Y reference axis. You will get this for the D sub Y, this for the C sub Y, and this one is for the C sub X. And you can see the measure of X sub X equal to 0. C sub X for sure is 0 kilonewton. And then if you can see the loading and the structure is in symmetry, you can see the C sub Y and D sub Y gonna be equal. You can prove it easily. Summation of the moment at C equal to 0, and you can see the beam is 2.0 meter long. So this D sub Y is going to rotate counterclockwise about C. So you got to have D sub Y times 2. And then what? And then you get this one equal to, this is going to be the resultant of the uniformly distributed load. That is going to equal the area of the uniform load. That is going to be 3 times 2. That is going to be 6, right? That is going to be, no, not 2. This is 1.60 meter. This is 3 times 1.6. 3 times 1.6 is going to be 4.8 kilonewton. That is going to be 4.8 kilonewton. So this one is going to be clockwise rotation. That is 4.8 kilonewton. And then time this distance, a half of 1.6 is going to be 1.6 divided by 2. Okay? And then by doing this, you will get D sub Y. Putting them into this is going to be, this is going to be 4, this is going to be 0.4, and then that is going to be 2.4 kilonewton. And then if you do the summation of F sub Y equal to 0, C sub Y plus D sub Y, this is 2.4 kilonewton, 2.4, that is going to be equal to 4.8 kilonewton. So your C sub Y is also 2.4 kilonewton. This occurs when the structure is symmetry. The reaction on the left and reaction on the right, they are going to be equal. Okay? And then next, we are going to cut this section. We cut this section at section AB, and the beam subject to what? Subjected to 3 kilonewton per meter. We have this one, this one. We cut it at 0.4 millimeter. This is 3 kilonewton per meter. This is 0.4 meter. And then you have this one for 2.4 kilonewton. And by cutting this, that means you're going to have this one for the moment M, and the shear here is V. Okay. And second, by the free body diagram of the section okay, here is a A to B. Okay, and then what? And then find V and M. Next, we can find the shear and find the moment. Then we have summation of F sub y equal to 0. Downward is positive, so V is downward. This one will have the resultant force again equal to area. That is going to be 3 times 0.4. Then it's going to be 3 times 0.4. That is going to be 1.2 kilonewton. And then this is going to be downward, right? In the same direction of V. This is going to be 1.2. And the upward is 2.4. That is 2.4. So we have the V equal to this one 2.4 minus 1.2. This is going to be 1.2 kilonewton. That is for the shear here is going to be 1.2 kilonewton. Then you do the summation of the moment here equal to 0. The counterclockwise moment is positive now, so our moment take here, and then it's going to plus 1.2. The distance here is half of this. That means it's going to times 0.4 divided by 2, and then that's going to be equal to what? This is counterclockwise, this is counterclockwise, this is clockwise, 2.4, and then times the distance here of 0.4. Okay, by putting them together, we will get the moment of 0.72 kilonewton meter. Okay, that is going to be 0.72 kilonewton meter. Then they ask us to use the equation that they given me from the chapter 7, from the chapter 6 to determine the normal stress and also to determine the shear stress. Okay, we're going to have this normal stress. This normal stress is only due to the moment, and they are asked us to looking for the shear stress. This is shear stress gonna be from this at what? At the point B. At the point B. Only at this point. Okay, as the point B. Anyway, I think it's better for us to draw the shear stress and normal stress distribution, because below this they also ask us to draw the normal stress distribution and also the shear stress distribution on this section. Anyway, due to the space limited here, I will draw the section and draw the stress distribution in this portion, okay, to make things more clear. Okay, this is 4 centimeter or 40 millimeter. Let me put this one in the scaling. Let's put this one for 2 centimeter. That is going to be scale of half of this. This is 4, this is 2. This is going to be 40 millimeter. And the thickness of this 5 millimeter, this is going to be 5 millimeter. That is going to be the top portion of this section, or this is top flank. And then it also have the web. Okay, the web is going to be 4 and 2. That is 6 centimeter. Half of that, let's put in 3 centimeter like this. That is going to be the portion of the web. And then we may put this one as the bottom portion. Okay, this is the flank. This is the outer section. This is going to be 5 millimeter, and this is going to be the total of 60 millimeter. This is 6 centimeter. Okay, this is half, and then the total of this length now is going to be the total of 70 millimeter. Okay, and we can see this is going to be the middle part of the neutral axis of our section, and this is going to be the centroid of the section. Basis upon this, that means we have this one for 30 millimeter and this one for 30 millimeter for this one. The width separate into two parts, and then based on the section that we are understand here, the section subjected to what? Subjected to the positive moment. That means what? That means it's going to have the compression on the top, and it's going to have the tension on the bottom, and in between the stress is gonna be in triangle. Why we know this? Because the stress that occur here is determined from the moment time what? Time the distance y and divided by the moment of inertia. Since the I is constant for a given section here, and also M is constant for a given section here, so the value of stress vary with the distance y. So this is the linear function. The top is going to be in compression, the bottom is going to be in tension, and it has the linear relation. What we have is this one, the stress on the top and the stress on the bottom, they must be equal because the distance 35 millimeter, the distance 35 millimeter, they are equal. This is going to be in compression, this is going to be in tension, this is also going to have maximum compression. Okay, this is going to have maximum tension. Okay, and then the B is what? The B is 20 millimeter. That means if you like, this is 30 millimeter. The B is somewhere here. This is going to be 20 millimeter. Measure from this one. Okay, and that means what? That means the top portion is this is 10 millimeter, and we can say that if we consider this, the B can be somewhere that you put the portion is going to be here, and the stress occur at this point is going to be sigma sub B. Measure what? Measure only 10 millimeter from here. Okay, if we understand this, we can determine stress at the point B. Sigma sub B is equal to the moment around here is 720 Newton, and then divided by the I. The I is here, we already computed, is 0.5133 10 minus 6, that is 0.51333 10 minus 6 meter powerful. And then this is what? This is 10 millimeter. This is 10 millimeter. So this is going to be in meter, 0.010 meter. You put this one into your calculator, you will get the stress here of 14.03 megapascal. That is the value of this is 14.03 megapascal. Okay, and also if you like to find the sigma max, can you find the sigma max here? Sure. You measure from this point to this point for the y. That means this is going to be 30 millimeter and 5 millimeter. That means you're going to measure for 35 millimeter if you like. Okay, you also can use the triangle to determine it. Okay, anyway, just put this one sigma max, that's in, is going to be the same thing, 720 Newton meter. Now the I still there, 0.5133310 minus 6, and the distance is 35 here, so it's 0.05 meter. If you put this one, you get this one for 49.1 megapascal. So this one going to be 49.1 megapascal. Or if you prefer, you may use the triangle. Okay, since you looking for what? Looking for sigma max here. You can see sigma max here divided by this length divided by half of this. So by using the slope, you will have sigma max divided by 35, and then it's gonna equal to what? It's gonna equal to sigma sub b. Okay, sigma sub b is 14.03. This is the formula divided by 10. Okay, if you put this one into your calculator, you will get the sigma max equal to 14.03 divided by 10, and then you times it by 35, and then you should get this one for 49.1 megapascal. So the value of sigma can be determined first by Flexural Formula, and then the other point due to is in the triangular, so you can use the slope to determine the stresses at the other point if you like to determine them. It's really easy and convenient to do so, right? Okay, and then you have what? You got to consider the transverse shear stress by doing this. The section is going to this one like this, and then again, like I put it in, I said it many times, the stress distribution for the I section is going to depend on a lot of things. The first thing is the equation that's used to determine it is tau equal to VQ divided by IT. Okay, on a given section, the V is going to be constant. Okay, the I is going to be constant, and then the Q and T going to be vary depend on this. And if you consider this section, the joint between the web and the flank have the different width. That means what? That means if you compute by using this equation, the Q will depend on what? The area here. Okay, so the moment of this area about the centroid of the section, the Q going to be constant. So the stress between this point is up to the width of the flank and the width of the web. Okay, that means what? If you divide it by the flank, the value of this is going to be small. Okay, let's say this is going to be tau 1. And when you divide it by the width of the web, this value going to be get larger. And this one is what? This one is 40 millimeter, and this one is only 5 millimeter. This one is only 5 millimeter. So the value here is going to be what? 8 times different. So this is going to get larger. Let's say this is going to be tau 2. Okay, and then the value of shear stress of the section will increase in the parabolic manner, and again the tau max occur at the neutral axis. Okay, that is going to be tau max. Again, due to the symmetry of the section, the top portion and the top portion, what we have is the stress distribution on the top portion. That is going to be tau 1 must be equal. This is tau 2 must be equal. And then the other portion, we will have this in the curve in the parabolic shape. Okay, for the shear stress distribution on this section, there you or me as got to determine tau sub 1, tau sub 2, and tau max. And this time they ask us to determine the tau at B. At this point. At this point is what? At this point is the point that we consider the section only in this point. And what we have from this is we set this one as the point B. And what we have is the tau. The tau sub B is going to compute basis on the shear here, 1,200 Newton. And then again, it's going to divide it by the moment of inertia 0.151333 10 6. Okay, and this is only what 5 millimeter. So the divider of this is going to be what? 0.005 meter. And the last one that we are looking for is going to be what? The Q. Okay, we should separate this section into two portions. The first one is this one, and the second one let's put into this one to determine the tau at this important, this asking point. And the Q is what? So this is this length. You cut it here. This is only 20 millimeter, and the width of this is only 5 millimeter. So the first one you will have 0.005, and then time what? 0.02, and then this is what? This is the centroid of this section. And then you got to take the moment of this section about the neutral axis of the section. So what we have is what? What we have is the distance here is 10 millimeter, and this is half of 20. This is 10 millimeter. So the total of this going to be 0.02. So it's the O2. This is the distance between centroid of this area to this. And you got to plus this one by the orange. This is 40 millimeter, and this is 5 millimeter, 0.04, and then 0.005. And then the distance here measure to the neutral axis is going to be the moment arm of this. And you know, half of this from this to this is 30 plus 5. This is going to be half of this. This is going to be what? The total is going to be 35. And then you got to minus this one by half of the thickness. So this is minus by 2.5. Okay, then this one going to be 32.5 millimeter. So the last one, you're going to have 0.0325. And then you put this one into the calculator. You're going to tau sub B of 3.97 megapascal. Okay. And then they ask us to draw the stress element at point B. At point B. At point B is subjected to what? this is the normal stress. Is subjected to normal stress. You have the normal stress in this direction. It's in tension because it's in the bottom portion in tension. This is 14.03 megapascal. Okay, and then the shear is downward. That means what? That means this stress is downward. When this one is downward, it's going to have this one upward. And if you take moment here, this is rotate this way, this is gonna rotate this way, and we have this one to balance this one, and we have this one for the tau. We have this one tau sub x y, because we said this one is x, this one is y. The tau is in both direction, and then this one is going to be 3.97 megapascal. And this one is what? Sigma sub x equal to this one. This one is in tension. Okay, that is going to be the stress element at point P. And if you go further, they like us to draw the normal stress distribution. Okay, this is finished already. Sigma Mech here is 49.1 megapascal. And this is 0. And this is compression in 49.1. And then they also ask us again for the shear stress distribution. Now, is this the question? What is the tau sub 1? What is the tau sub 2? The tau sub 1 there is also tau sub 1 here. The tau sub 2 here is going to be tau sub 2 due to the symmetry of the section. Okay. By doing this, they ask us to indicate the stress. For this is okay, maximum and minimum. Okay. For this one, the maximum is here. Even though you know the maximum, you still find the tau sub 1 and tau sub 2. Okay. This is start by what? Let us start by find the tau sub 1. Okay. If you like to, tau sub 1. Tau sub 1 is what? Tau sub 1 is based on the computation of the V Q over IT of this area. So this is going to be the same thing, 1,200 Newton. And then divided by what? Divided by the same thing. Divided by I. Okay. And then divided by I. And then what? Tau sub 1 is based on the flank. Tau sub 1 is based on the flank. Okay. That means we're going to have the width of the flank. So the width of the flank is 40 millimeter. This is 40 millimeter. So this is 0.04 meter. Okay. So the Q of this green and the Q of this yellow, they are going to be the same. So the area here, 0.04 times the thickness, 0.005, and then the distance from this one to this one, right? So it's going to be what? It's going to be 0.0325. So this is 0.0325, and then you just close this one, and then you have this one for what? For tau 1, 0.379 megapascal. 0.379 megapascal. See, this is a lot smaller than this one at tau sub b of 3.97. Anyway, the next one, you got to determine tau sub 2. Okay, tau sub 2 is based on the width here. And you can see the ratio of the width. This is 40. This is what? This is 5. Okay, you may see this is can be computed by 0.379 and then times 40 divided by 5. You can compute this one easily. Tau sub 2 is going to be 3.064. This one is supposed to be 3.064 megapascal. That is 8 times larger. Ajahn, I don't believe it. If you don't believe it, you do the calculation as before on the top. Just to change this one into the thickness here of 0.005. Everything here the same, here the same, Q the same. You will get the same answer here. So it's up to you. Okay, you may put this one 1200 times the same value here, and this one also 0.5133310 minus 6 and the same Q. See, there are only the difference between this portion, and the width of this portion. Okay, and the last one, we kind of need to compute the tau max. When you compute the tau max, what we have is you got to compute based on this total area. Okay, so same thing, tau max still come from the same thing, V the same 1200 Newton divided by the same thing, the I is 0.51333, and then 10 minus 6 meter power 4. And here the width is only 0.005, so 0.005 meter. So the Q. The Q here, the Q for the green and the Q for the yellow is the same thing. Okay, you just put the same one over here. That is going to be the area 0.04 times the width 0.005, and then times the distance here 0.0325, and it's going to plus for what? The area, the pink area 5 millimeter and 30 millimeter 0.005, and this is 30 millimeter, so this is 0.030, right? 0.030. Okay, ถูกต้อง sorry, it's correct. 0.030, 0.005, and then what we have is this one is the centroid of this pink area measure to the neutral axis of the section. That is half of 13 millimeter here. So it's going to be what? It's going to be 15 millimeter. So it's going to be 0.15 meter. You put everything together, you will get tau max equal to 4.116 megapascal. Okay, that is what should we have for this portion. Okay, I did drawing the normal stress distribution and shear stress distribution into this. And if you may recall, sometimes the maximum shear, they just ask us approximately to determine from the V divided by the area of the web. Okay, if you take a look at this one total is 60 millimeter. This is going to be 60 millimeter. The thickness here is going to be 5 millimeter. The tau max can be approximate to be what? To be this one is 1200 Newton, and then divided by 60 and times 5 millimeter square. You cut this one, okay, and 6 cut this one going to be what? 120 divided by 6, this one going to be 20, and then it is going to approximately 4.0 megapascal. It can be approximate like this for this section. Okay, That is everything that we like to have, the normal stress distribution, the shear stress distribution, the maximum, the minimum, and some important the stresses as the important point. Okay, and I also ask you again to draw the stress element. For example, at this point, let's say if this one is going to be 10 millimeter, okay, and this is 5 millimeter, what is going to be the stress element here? That is for your quick assignment.
For this example, we like to determine the flexural stress and transverse stress distribution on this reverse T section. Usually, the T section is like this, but in the examination, Ajahn just reverse the section to be like this. And basis upon this, they provide us with the position of the centroid to be y equal to 36.25 millimeter. Okay, if not, you got to find this by yourself. So go back and review how to determine the centroid. And also, basis upon this, there is going to be the neutral axis over here. This is going to be the same neutral axis over here. And the problem provide you with the moment of inertia about this neutral axis. So if not, go back and determine it. From this problem, the problem is the cantilevered beam. So you don't need to determine the reaction force and the reaction moment at this support, at this fixed support. Just cut this section and you may determine the shear at this section and the moment at this section for a given AA section. Okay, and then from the free body diagram that you have, you just cut the section and then let's set this one, this X, and this one is Y. You can determine the summation of F sub Y equal to 0. Upward is positive. So the V is going to be upward, and -2 -4 equal to 0. So the V is going to be 6 kilonewton. And then you just take a moment over here and you can measure. This is going to be 0.25 meter and this one is going to be 0.3 meter. Just put the distance into the free body diagram. Since when you take the moment, the summation of the moment with the counterclockwise direction is positive. So the M is positive in this way. And you can see the moment from the 2 kilonewton will be rotated. So 2 kilonewton times 0.25. And then the moment is also going to be equal to 4 kilonewton times the distance over here is going to be 0.55. You get the moment into 2.7 and the moment now is in this direction. That means it's going to be the negative moment, and then this is going to be in the compression in the bottom. You put it in this way. Okay, compression is in the bottom, and then you get the top is going to be in tension. Okay, so next, basis upon this, we can determine the maximum stress easily. is going to be based on this distance. Okay, we have the total over here to over here of 90 millimeter. So over here will be in millimeter 90 minus 36.25. Okay, and then you will get this distance to be what? 90 minus 36.25. 90 minus 36.25 is going to be 53.75 millimeter. So we will use this distance to determine sigma max on the top, and on the top is going to be in tension. Okay, so we have M Y top over I, and then we get this one to 81.25. And then for the compressive stress that's going to occur on the bottom, we use the pink distance. We get this one to 54.75 is in compression. So this one in tension. You may draw this one for 8.1 millimeter, and you may draw this one for 5.5 millimeter, and you do the stress distribution. This point is the point of zero stress. And then the tau max, as you see from my sketch, this section is going to has the reverse shear stress distribution. Let me draw for you guys again. The top and the bottom must has the zero shear stress, and since this is the web have the frank has different thickness from the web. That means the stress distribution occur over here. Okay, occur over here. This one will basis on this width, and then due to the different, this time they are different by what? They are different by the thickness of the section. The frank 50 millimeter, the web 20 millimeter. So the ratio of the difference between frank and web is going to be 50 divided by 2. So that is about 2.5. Next, the stress that occur over here, okay, will be larger than occur over here by 5/2 times. And then the maximum stress will occur at the neutral axis. So this one will increase a little bit to reach over here to be the tau max. And then the stress distribution for the rest of it will similar to the rectangular section. This one, okay, will similar to the rectangular section. And then if you like to determine the tau max, over here, okay, the tau max will be the V at AA section time Q over I, and then divided by the width of the web. Okay, this is going to be 3 web. So the T web is 20 millimeter. We know the I. We have compute for the V over AA section, and the last one that we got to determine is the Q. The Q can be determined based upon this green area, or you may use this bottom area to determine the Q. But the yellow area divide into 2 portions, so it's not convenient to use this bottom yellow area. So based on this, the Q will based on this area with the width of 20 millimeter and the depth of 53.75 millimeter, and then this is the moment of the area about the neutral axis. So the distance here is going to be this one divided by 2. So you get this distance, okay, by 2. You get this distance, and then just put them together. You get the 4.85. And since this shear force is upward, so the shear stress will be upward also. And this is going to be the maximum how occur on the section. Now you can draw the stress element. If you prefer to find the stress element on this portion, or you may say is over here. The stress over here is in tension. So we got this one as the stress distribution. Next, if we consider to determine the stress element over here, the stress element is a representative of the material at that point. This one is subjected to compression. So this is going to be the stress element over here. This is going to be the stress element over here. How about the middle? So over here we have the upward. Okay, we're going to change this one. We have the upward stress distribution. The maximum is in the what is in the neutral axis. So over here, the stress distribution, I got to change it a little bit. This one must be upward, and this one must be in this direction, and in this direction, and in this direction. Okay, and then if you just prefer to find the stress distribution at this point, or you said at this point, so at this point it's going to get in compression, and also the normal stress over here. So this is going to be the stress at this point. And then if you just prefer to draw the stress element at this top of the flank, so this one will be in what? In compression. Okay, and then it's going to be in the shear stress with this smaller value. So you may just draw this stress element. So you can draw any point